Friends, very good morning. How do you do? Are you enjoying all the sessions? Okay. Let us see today the various computations of gradually varied flow. In the last class just we have enlisted what are the various methods such as numerical method, simple and advanced numerical methods, graphical method, direct integration. Under numerical method, there are two, direct step method and standard step method, whereas only direct step method in which the numerical problem is included. Okay? So these we have already seen. Graphical method is practically nowadays obsolete, and direct step method is the one which will be helpful for us to understand the various water surface profiles, how much long or how long they occur on the upstream side, so that the remedial measure could be undertaken. Okay? Now, the differential equation of GVF is a nonlinear first order ordinary differential equation that we know. That is dy by dx is equal to s naught whole multiplied by 1 minus yn whole cube yn by y whole cube whole upon 1 minus yc by y whole cube, or dy by dx is equal to s naught minus sf divided by 1 minus q squared t by ga cube. What are what? S naught bed slope, yn normal depth, y depth of flow, yc critical depth, sf energy line slope, q is the discharge, t is the top width, g is acceleration due to gravity, and a is area of cross section of the open channel. There are several methods of direct integration of GVF equation. Bresse's method for wide rectangular channel, VenteChow method, Kiefer and Chu's method for circular channel. Okay? Methods of GVF computations, direct integration method. If k is equal to conveyance at any depth y and k naught conveyance corresponding to the normal depth yn, then when flow is GVF, k is equal to q root sf. When flow is uniform, k naught is equal to q root s naught. Hence, sf by s naught is equal to k naught by k whole squared. B. If z is equal to section factor at depth y and zc is the section factor at critical depth yc, then we can write down z squared is equal to a cube upon t and zc squared is equal to ac cube upon tc, that is equal to q squared by g. Hence q squared t by g a cube is equal to zc by z whole squared. All these equations you have to write and practice, then you will remember. Please do the practice at home by writing on paper. While listening to the lecture, it seems to be very easy. Steps are very easy. But to remember, until unless you write on paper with concentration, understanding each and every parameter, it may be little bit difficult. Okay, students? Now, rearranging GVF equation, we can write down dy by dx is equal to s naught minus sf divided by 1 minus q square t by ga cube, that can be rewritten as s naught whole multiplied by 1 minus ko by k whole squared divided by 1 minus zc by z whole squared. Okay? Let it be required to find the depth of flow in the open channel y is equal to f of x in the depth range y1 to y2. Say, for example, the following two assumptions are considered in the solution. K is equal to conveyance at any depth y and k naught conveys corresponding to the normal depth yn. Therefore, k is equal to c2 y to the power of n when flow is uniform. K0 is equal to c2 yn to the power of capital N. Similarly, z is equal to the section factor at depth y and zc section factor at depth corresponding to the critical depth yc, and it is given by z squared is equal to c1 y to the power of m, zc squared is equal to c1 yc to the power of capital M. Is it clear? Now, GVF equation becomes dy by dx is equal to s naught whole multiplied by 1 minus c2 yn to the power of n divided by c2 y to the power of n whole upon 1 minus c1 yc to the power of m divided by c1 y to the power of m, or dy by dx is equal to s naught whole multiplied by 1 minus yn by y whole to the power of n divided by 1 minus yc by y whole to the power of m. Now, if y by yn is equal to u, then dy is equal to yn du, and the above equation can be rearranged as yn du divided by dx is equal to s naught whole multiplied by 1 minus 1 upon u to the power of capital N whole upon 1 minus yc yn whole to the power of m. Now, GVF equation becomes du by dx is equal to s naught whole multiplied by 1 minus 1 upon u to the power of capital N divided by yn multiplied by 1 minus yc upon yn whole to the power of m multiplied by 1 upon u to the power of capital M, or dy by dx. Ultimately, we will get this equation. I need not have to read, I already read. Rearranging the above equation, we get dx by du is equal to, instead of du by dx, let us take 1 upon it. That means dx by du is equal to yn divided by s naught whole multiplied by u to the power of n minus 1 divided by u to the power of n minus 1 plus 1 upon u to the power of n minus 1 minus yc by yn whole to the power of m u to the power of capital N minus capital M divided by u to the power of capital N minus 1. Or integrating the above equation, we get x is equal to yn upon s naught whole multiplied by u minus integral of 0 to u du by 1 minus un plus yc by yn whole to the power of m integral 0 to u to the power of n minus m divided by 1 minus u to the power of n du plus constant. Direct integration method. This is also not included for numerical problems, just direct integration method is included. VenteChow method. This also in the same similar manner as we have done for the previous one. This is Brace's method for wide rectangular channel, right? These are not included as per your syllabus. However, for gaining more knowledge, if you are interested, you can go through in detail on your own. It is not of much difficulty. The steps are very nicely narrated. Okay? So I do not wish to carry out this because it is not included in the syllabus. Now the graphical method. of integration of varied flow equation can be used for both prismatic as well as non-prismatic channels. It uses different values of y, and computation can then be carried out graphically. GVF equation is given by, we know, dy by dx is equal to S0 minus SF whole upon 1 minus q square t Ga cube. For computation, rearranging the equation, we get dx by dy is equal to 1 minus q square t divided by Ga cube whole upon S0 minus SF, just 1 upon. Since for a given discharge A, T and SF are functions of the depth of flow y, we may write dx is equal to f of y into dy, where f of y is equal to 1 minus q square t divided by Ga cube whole upon S0 minus SF. Now, if y1 and y2 are the depths of flow at points x1 and x2, from the control section, what you have studied in the previous slides, then by integrating, we get x2 minus x1 is equal to integral x1 to x2 dx, that is equal to y1 to y2 f of y dy, f of y dy, dx is equal to f of y dy. This one should be here. Now, methods of GVF computations. Graphical method. By assuming several values, this figure indicates all the parameters which have been taken on abscissa and ordinate. By assuming several values of y, the corresponding values of fy may be computed. A curve of y versus a curve of y versus f of y is then prepared, and the area under the curve between y is equal to y1 and y is equal to y2 is determined, which will give the longitudinal distance x2 minus x1 required for this change in the depth of flow in accordance with the equation. If y1 and y2 do not differ much, then approximately x2 minus x1 is equal to f of y1 plus f of y2 divided by 2 multiplied by y2 minus y1. You look at the figure also, everything is clearly written. Direct step method. Now, this is one which is being used as per the syllabus to find out the total length of occurrence of any surface water profile so as to monitor on various practical applications. This method is possibly the simplest and is suitable for use in the prismatic channels. You know what is prismatic channel? The one which has no change in the depth or width or any cross section throughout, including the slope bed. So bed slope also is constant or consistently same. In this method, the length of channel is divided into number of short reaches. You can see here. Short reach means what? Considerable least distance. Say x1, then x2 or dx1. In order to understand, we put dx1, dx2, dx3, dx4, etc. Okay? Short reaches, and computations are carried out step by step from one end of the reach to the other end. Means this is 1-1, this is 2-2, this is 3-3, this is 4-4 section. Okay, from 1-1 to 1-1 section to 2-2 section is dx1. From section 2-2 to 3-3 sections, dx2, and so on. Consider a short reach of channel in section 1-2 of length dx. So let us understand the whole procedure for one short length, that is dx, and then Any number of such lengths dx1, dx2, dx3, etc. can be calculated by using the same steps and procedures and formulae, and then you take sigma. Sigma means this sigma. Mathematical this sigma. This sigma means total summation. Total sum. Okay. Assume length of the reach dx is small and profile of reach can be considered as straight line. So until unless we assume, it is not quite possible to consider the profile as straight. Since dx is very, very small, let us assume small. Then conveniently we can understand it is the straight line. Apply Bernoulli's equation as you know. Z1 plus Y1 plus V1 squared by 2G must be equal to Z2 Y2 V2 squared by 2G plus HF, where HF is the loss of head due to friction. Z1 plus E1 is equal to Z2 plus E2 plus HF. We can rewrite it. So therefore, dx is equal to E2 minus E1 divided by S0 minus SF. Ultimately, this equation becomes this. Figure which you have already seen and learned in the previous classes. So, using above equation, dx1, dx2, dx3, etc. can be computed and total length will be given by x is equal to dx1 plus dx2 plus dx3 plus dx4, etc. The computation are carried out in upstream direction in case of subcritical flow, downstream direction in the case of supercritical flow. This we have to remember. Upstream direction in case of subcritical flow, downstream direction in case of supercritical flow. Okay? Now, procedure. How this direct step method is being followed in order to find out the length of occurrence of any water surface profile in the open channel. For computation of dx, following quantities should be known. What are those quantities? 1. Discharge Q, channel shape and width. Channel shape, whether rectangular or trapezoidal or circular, etc. Bottom slope, say S0. Roughness coefficient, rugosity coefficient, small n or capital N or small n. Depth of flow, Y. At any section, generally control section we make use. Now, we will see the steps. Okay. Step 1. Carefully observe. Whatever the steps we are learning here, based on the same steps, we will solve the numerical problem. Okay? We will solve the numerical problem. But whatever theoretically we learn, that we write down in the form of a tabular column. It consists of around 13 to 14 columns. Not difficult. Very easy. Only thing is you must understand these steps very carefully. Okay? Step 1. First of all, you compute the area of flow. Compute the area of flow. A. Wetted perimeter P. Hydraulic radius R at the section where depth is known. Also compute Yn, that is normal depth, if not known, and define the type of profile. Step 2. Compute average velocity V. Compute average velocity V. Velocity head, that is V squared by 2G. And then specific energy E at the section where the depth is known. Also compute slope of energy line SF using any one of the equation depending upon Chedji's formula and Manning's formula for finding out velocity. So we know that V is equal to C under the root R SF, where SF is equal to V squared divided by C squared multiplied by R, where V is the average velocity, R is the hydraulic mean radius, and capital C is Church's constant. Similarly, if you use Manning's formula, then you will get SF is equal to, that is slope of the energy line is given by the ratio of n squared V squared divided by R to the power of 4 by 3, where small n is nothing but equivalent to capital N, that is rugosity coefficient, V is the average velocity, and R is the hydraulic mean depth, that is area by wetted perimeter, capital A by P. Next, step 3. Another 2 steps are there. That's all, very simple. We can solve the numerical problem quite easily. Assume new depth at any other section. This section should be close to the first section. That's all. Suppose you are considering in an open channel, first section, second section, that is dx we have assumed. Similarly, you take another section 3, that should be very close to this. That's all. That is the meaning of that. Also, increment in the y should be small. Then compute all above quantities for new assumed depth. That means y, y1, y2, etc. As we proceed, the depth may be different. So corresponding depth should be considered, and all the parameters, all the quantities should be calculated as before. Then compute all the above quantities for new assumed depth. Then step 4, compute delta E is equal to E2 minus E1. Here wrongly printed E2 minus E1. This should be E2 minus E1. Please correct yourself, students. Step 5, compute average SF. Average SF. What do you mean by average SF? That is mean value. SF1 plus SF2 divided by 2. Use same average SF in equation of dx. Step 6, compute dx using dx is equal to length of curve between the two sections. Means section 1, and section 2. Section 2. This is dx. Okay? This is dx. E2 minus E1, that is difference between the specific energy. So here he has written correctly, is it not? So in the previous case, E2 minus E1, instead of E1 it is being E2. Okay? Now it is being corrected in this slide. E2 minus E1 divided by S0 minus SF. Step 6. Repeat the above steps from reach to reach till the required depth is reached. That's all. Here, useful hints. We'll take this in next class by revising that also. Whatever the steps, once again we will go through, and then we will come back to actual hints. What are all then? Standard method. Okay, we will see in the next class. Thank you. Have a nice day. Have a nice day. Goodbye. Have a nice day. Please do keep practice. Please do keep practice. Okay? Don't forget that. Please do practice.